Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Jim Zimbelman with us today. Hello, Jim.
Hello.
Well, first of all, thank you very much for agreeing to talk about your very awesome PSJ article.
I look forward to discussing it.
Cool. And we will get there. And Jim, where are you located at?
I am sitting right now in Manassas, Virginia, which is about 20 miles outside of DC proper. I worked for 32 years at the National Air and Space Museum. That's where my research was through that medium. And I never imagined I'd work at a museum, but it has been a fabulous place to be.
Awesome. Very cool. Very cool. And it is July 7th of 2023 as we record this. And how is the heat and the humidity in the Virginia, Manassas?
Both are up, not surprising. This is a July in the DC area. That's what you get. Yeah, but it's not like Phoenix heat.
Yes, I am in Phoenix. I'm at Arizona State University, and somebody has definitely turned on the power switch. We are hot. But I understand that you also graduated from ASU.
Right. So I know what Phoenix heat is like. My PhD program was there at Tempe. Ron Greeley was my advisor. And I went to ASU to work with Ron because Ron not only is a good geologist, but a planetary geologist, which is what I wanted to be.
Excellent. Very cool. And you can tell that because you have some very awesome globes over your left shoulder there. Yep.
All the way.
Look at that. You got them all. That's great. That's fantastic.
And not surprising, those are planetary globes. One is the Earth, but I've got Venus, couple of Mars, Jupiter, Pluto, and Mercury.
Wow, Pluto. That one might need some updating in a bit. And Mercury is a hot topic these days. So very cool. And Jim, as you learned from one of the masters on how to be a planetary geologist, what kind of research do you like to do?
Not surprisingly, my interests are still aeolian, which is wind surface interactions, and that's what the paper's about.
Very cool.
And also volcanism. And it's because Ron was funded by NASA to study aeolian processes in the solar system and volcanism in the solar system. It stuck. That's what I was working on, and I just loved it.
Well, it's a great topic. It's got lots of applications as we will venture out into the planetary system. So very cool. And that is going to bring us to this very awesome PSJ article. It's open access. We are in the open access era, people. You can go grab a copy for free. Go get one. Aerodynamic roughness height of gravel-covered plains in the Puna of Argentina. And Jim, take us away.
First, let me explain what those first three words are.
Okay.
Aerodynamic roughness height is simply a number that refers to how the surface is interacting with the wind profile. And we won't go into the gory details, but imagine an airplane wing and friction with that wing causes drag on the plane. You don't want that. Well, nature is sort of doing the same thing. And the features I want to study here, the gravel plains in Puna, have very large particles, very large being a couple of centimeters.
Okay.
For aeolian studies, that's big.
Yeah.
Why? Because it's really tough for the wind to get those things to move, and yet they clearly have in Argentina. So my co-authors here, Mauro works in Argentina, and so it was great to have a local, but Sean is really the instigator behind this. Sean has studied volcanism in South America literally for decades. And he saw these aeolian features when he was in this area of the Puna looking at a volcanic problem and said, we got to investigate this. And I was very interested in large aeolian wind features, which we can go into gory detail if you want.
This is a journal article. You can go in as much gory detail as you want.
This was all stimulated by, in 1999, the Mars Global Surveyor spacecraft got to Mars and showed us pictures of Mars where there were clearly wind features, but it was a better camera we had ever had at Mars. So the question was, is that a large wind ripple or a small sand dune?
Okay.
And those sound like the same thing, but they really aren't. And so that's what stimulated all of this. To begin addressing it quantitatively, we needed to study these things on the ground. And Sean had found a site with some of the biggest wind features I've ever seen.
Wow, very cool. And in fact, why don't we go ahead and take a look at that site? Let's take a look at that site. Gorgeous, gorgeous, gorgeous. Puna.
It is startling. You feel like you are on another planet when you're out in these plains. Now, most of the colors you're seeing are related to, it's virtually all volcanic bedrock. Volcanoes produced the whites, the darks, the reds, all of those things. But the wind has been the dominant agent in the last tens of thousands of years. And so that's what generated the large wind features that we wanted to study. And we'll see what one of those looks like when we get further down in the figures. But the 5 letters are the 5 locations where we did wind profiling. And all that word means, wind profiling, is that we had anemometers on a rod at logarithmic spacing and measured the wind speeds at those different spaces. And through processing that data, you get a 0 point, and that is called the aerodynamic surface roughness height or length.
Makes sense. And dare I ask, how did those sites get their letters?
It's the names, and they're summarized at the caption there.
Here we go. Here we go. Okay, there we go. CPP.
And CPP, for example, it's Spanish, so I'm going to slaughter it, but it's Campo Piedra Pumice.
Okay.
So that's plains of pumice, basically, which is a pretty good description.
Absolutely. And just for scale, in case people can't see it, this is a scale down here. That's about 8 kilometers on this air bar, on the scale here. So you can get a sense of the total dimensions of the image here. Very nice.
And to me alone, it would have been very intimidating to get to one site, let alone these 5. But Sean is so used to working in the Puna. He drove, he knew what he was doing. We didn't get stuck. I would have gotten stuck zillions of times.
What's the elevation of this site?
Good point. Very, very high. The average is about 3,200 meters.
Ooh, okay.
We're in the 14,000 or so foot range, 11 to 14. And a lowlander like myself notices it. Sean is pretty used to it from his decades of work, but it took me days to really begin to feel sort of comfortable at that elevation.
Very nice. Very cool. All righty. So let's see what kind of science we found there.
And the elevation is important because that lowers the pressure. That's a good thing for us trying to relate this to Mars, for example. Mars is even a lot lower pressure, but it helps to just be at a high elevation site.
Very good. Okay. Earth analogs. Okay, let's slide down. Let's take a look at some of these wind speeds, shall we?
And we won't go into the details here, but this is a tabulation of the wind speed measurements. That's the V average, third column there, as a function of height, the 5 different anemometers at the multiple sites. And we had 2 towers at each site.
Okay.
The numbers, that's wind speed, but then right next to it, it's labeled Z0. That's the number we were after. And what that number means is using those 5 or sometimes 4 wind values, you can extrapolate, fit the curve, and extrapolate to where you get 0 velocity.
Okay.
What height that is. And that is the aerodynamic roughness height number that we're after. It varies quite a bit as you're looking through the table. There's a variety of reasons for that, but you'll see a lot of 1s, and then a couple of 2s, but not many 4s or higher. And that's kind of the punchline, that we specifically went there to study these large wind features, but nature has a way of sort of evening things out. And as long as we weren't literally on top of one of the large ripples, we got very similar numbers throughout the Puna study area. That was a surprise to us. Now, we did begin to see the effects of these great big wind forms when we get to these 2s, 3s, and 4s. The 0 point in the wind speed is a bit higher, and we think that we hypothesize that is because of the actual shape of the mega ripple form. It's
Okay.
altering the wind flow, just like wind would go over a bump or
Yeah.
a curvy surface or something.
Okay. Cool. A couple of questions, if you don't mind.
Sure.
So Z0 would have, well, it's a zero height, but
It's
so
all in centimeters there.
centimeters. We're good. Okay, I'm good there. And my second question, does the Puna have a prevailing wind? Is the wind always blowing in one direction, or is it
Oh,
swirling around, or what is it? What's the general wind pattern there?
great question. The soft winds, being 1 meter per second or less, they came from all over the place. They were pretty squirrely.
All
But
over.
the afternoon dominant winds were from the sort of northwest, and they were pretty consistent.
Okay.
And so we tried to get set up so that we could take advantage of those stronger afternoon winds. And that's what the ripples were oriented relative to, those stronger winds.
Oh, that's good. That makes sense then. Okay, good.
Yeah.
We're consistent.
Yep.
Very good. Okay, onwards. We had the winds. Oh, and here we go. Let's take a look at
And
what
this is what it looks like. So the view at the left, that is looking straight down on top of one of these mega ripples. Now, why do I use the word mega? Because these things really are much bigger than, say, a wind ripple you would see on a beach. And the wind's blowing and makes ripples that have like a 10 centimeter or so wavelength.
Yeah.
These things have wavelengths on the order of 5 or 6 meters.
Meters. Wow. Cool.
The height of a typical sand ripple is 1 centimeter. These things range from 40 to 60 centimeters in height.
Wow.
So you definitely know you're walking over a bed form when you're walking on these things.
Very
so
cool.
the view on the right is in between
Ah.
the mega ripples. So it's the same kind of particles, although just comparing the two pictures, you can see that the things on the crest of the big ripple, those are actually coarser particles. They tend to concentrate at the very top. Why? Because that's the fastest wind speed.
Yes.
And they can move the bigger guys. And once they get up there, they just sort of huddle and stay there.
Interesting. How interesting.
And on the right, you notice things aren't real close together, but that is also because of the wind. There is a spacing that naturally occurs when you have larger particles.
Yeah.
And they sort of naturally space themselves out. That's what you're seeing at the right. Why? The simple answer is, what is moving these things? It really isn't the wind, it's the sand being blown by the wind that impacts on the particles and causes them to move. Well, think of, if you can see my picture here, the sand grain goes straight up and then has this very curving trajectory.
Okay.
It hits. So it's that shallow slope at the end. That surface on the right is effectively armored. That is, the sand grains never see the intervening sand.
Fair enough.
On that low angle, all they see are the rocks and keep hitting the rocks and bouncing very high.
Got it. Very nice.
But on the ripple crest, they get really close together.
Very nice. Cool. Okay. So we have some measurements. We got some results here at our different towers, complete with some very nice geolocation data. I won't attempt to butcher my Spanish there. Oh, and here we go. Here's more of a global tower.
And that sort of helps you see what we were doing.
Okay.
This was a location where the wind literally was blowing so strongly that I got one of our field people to hold on to it. I was afraid it would literally blow over my lightweight mast.
Yeah, you only got
lightweight so I could carry it easily, but we were getting 15 meter per second winds. That's like 30 some miles per hour. And the thing was just wobbling enough that I just felt much more comfortable having someone hold it. And we would do measurement runs of, say, 20 to 40 minutes.
Okay.
And the guys could do that, could manage holding on for 20 minutes.
Okay. Just to get a sense, these were not remote, unpersoned stations.
Nope. And the tripod between me taking the picture and the tower with the anemometers, that is holding 5 handheld devices, which is actually doing the measurements. Yeah. So each one had a little like a photo card for a camera. stuck into it, and every 2 seconds it was recording what the wind speed was for each anemometer.
Value here, actually, if you look carefully on that top one there, you can actually see a number on that. Very cool.
Oh, that I added just so I could keep track of which anemometer was at which height location.
Okay, okay, very good. And what is the white arrow pointing to?
That is this dominant wind direction, the thing that you had asked about.
Okay,
and it was blowing like the dickens, coming from the direction the arrow is indicating. So you see the larger ripple crests to the right of the arrow.
Yep.
We had set up, in fact, to measure the mega ripple that's at the far left. That was not the wind it was following today.
Okay. Wow. Yeah, it's definitely a striking pattern. Very cool.
It is, but at least we felt the measurements were good because we are far enough away from the crest. There are aerodynamic effects right at the ripple itself that we didn't want to be in, and we were far enough away where we had set up the tower, and we hadn't disrupted the surface between the tower and that ripple that is upwind of us.
Okay. Okay. And at any given location, we did multiple measurements, or we went out one day and did one measurement, or how did we?
Because of the difficulty of getting to these sites, it was typically one run at each site, but we had 2 towers and compared the results.
Good. Okay. Very nice. Okay. Number 3, and then we have some actual data here. So let's talk about wind data.
And the main point of this is to just show how gusty the wind was. It wasn't a constant, steady wind, but the vertical axis there is wind speed in meters per second. This varied fairly rapidly. The horizontal axis is hours and minutes. So in between each vertical gray line is 3 minutes. It was variable on tens of seconds timescales.
Wow. Yeah.
But if you bother to correlate the colors of the dots with our different anemometers, we were getting reasonably consistent results.
Okay.
There were exceptions, like just to the, well, above the 1729 number, one of the anemometer speeds really dropped off, but then it picked up again. I have no idea why. But what we did to get our number is averaged over the entire time period. In this case, what was shown here.
Yep.
And that average gave a reasonable correlation coefficient across the entire sweep of the wind data.
Yeah, very nice. Very nice.
And if people like figures like this, where in the methodology where we describe what we've been doing, there are links to all of the raw wind data every 2 seconds, every anemometer, every tower, if someone wants to delve into it, plus a whole bunch of additional field photos that we couldn't fit into the short paper.
Open data is a good thing, open access, so you can go grab the data, people, if you want to go. Very nice.
That's what we want.
That's definitely what we want. And then we end off with a motley crew here.
Yes, and this leads to, I said Sean's been working in the area studying volcanoes for decades. We've been studying these mega ripples for about 15 years. And it's a little hard to see, but there is a white scale right in the center of the picture.
Right here.
And next to it, to the right of it, is a black line. That is a nail that I hammered into the crest of the mega ripple in 2010, our first visit.
Okay, okay.
And the Mauro, the Argentinian on our team, would go out more often than Sean and I were able to go there. And by the way, the other people are students, either Sean's or Mauro's students coming to help us.
Very
well,
nice.
up to 2016, Mauro had seen 0 movement of that nail. It was still on the crest.
Okay.
Well, between 2016 and 2018, when we were there, and that's what the paper results are about, this particular mega ripple moved 30 centimeters.
Yes, because, okay, so originally it was basically on top, and you can already see it's not on top anymore.
Right, and that sort of gives you an idea of the height near the crest.
Yeah.
The nail, we tested it. It was still firmly implanted. It's a long nail.
Okay, okay.
And the top of the nail is where the top of the mega ripple was 8 years before when we emplaced it, and only 2 years before the last time Morrow had visited. So what happened in those intervening 2 years? Well, Morrow has been trying to make a longer term anemometer study, not for profiling, but just what the kind of daily to monthly wind cycle is.
Okay.
He's been having issues, and we don't have the exact date for when this happened, but there is other field evidence that there was just a horrendous windstorm between 2016 and 2018, perpendicular to the ripples. The mega ripples are transverse to the wind flow direction.
Correct.
And that's what the white arrow indicates.
Yep.
But the wind was so strong that it moved these things.
Wow.
Now, in the background is a pile of rocks.
Yes.
That was placed, we don't know when, but it was on the side, the windward side of the ripple whenever it was in place. From our one measurement here of how much the mega ripple moved in 2 years, we infer that that pile of rocks was probably in place 60 years ago. Either very preliminary or rudimentary motorized vehicles, or maybe even camels, or who knows what the Argentinians, the llamas or something to move around there. But it was some kind of marker. And the marker stayed, but the mega ripple has bent around it.
That's great.
In that intervening year. So this convinces us, this one picture convinces us that things are happening, but not on an annual cycle. It's more on a decadal cycle.
Right. Right.
Oh, and behind the guy at the right side of the figure is the next mega ripple. That gives you an idea of the spacing at this area. These were the biggest ones in our particular field study at this time.
Like trough to trough there, and how big
that's more like 15 meters.
Yeah. Okay. Right. Given the size of the people here.
Yeah.
Yeah. Very cool. Very nice. Very nice. And we go off and a little more of the particulars, and then we have a discussion. And
if you're familiar with papers, when you get to discussion, that's where we can wax a little more not eloquent as much as we can hypothesize. And that's exactly what we tried to do with that nail. And why are we so interested in getting a rate? Well, if we can understand here on Earth the cycle and when these strong wind events happen, we might be able to translate that better to Mars. Why Mars? Well, that's what stimulated all of this in the first place. That the figures that showed up in those very early Mars Global Surveyor images, we're still debating, although I think most of the community is now comfortable calling them a mega ripple. They are not a sand dune, not a typical sand dune. They are a large wind ripple. And it's just the time scale on Mars is probably much different than even what we're talking about here at the Puna. It could be, I don't know, centuries between a wind event that is strong enough to actually move a centimeter-sized particle on Mars.
Yes, although, Mars does have these occasional very large global windstorms.
Dust storms, yes. But what is this wind doing at the surface? We have very little information until recently. A couple of the rovers are finally measuring that. We have not seen like horrendous hurricane strength storm events on the anemometers that have survived. But it's a difficult environment. The Curiosity anemometers were broken by saltating sand, so that the sand was getting high enough and going fast enough that they damaged the sensors. And Perseverance now has a more robust set of anemometers on it.
Very nice. Very, very cool. Very nice. So Jim, thank you so much for walking us through this very awesome PSJ article. Very nice. So you touched on it a little bit there with new anemometers. And so let me ask, where do you think we go with this topic over the next 2 to 5 years? Are there other sites besides Argentina that might be useful as Earth analogs for some of these? You mentioned some sensors on Mars. Are we planning on putting more sensors on Mars? Or how about Titan, or maybe some of the other planets, and where we go? So Where do we go with this over the next couple of years?
Well, let's start at the beginning. You asked things that could keep us here for hours, but
Oh, great, great.
But the next several years, I think it is worthwhile Mauro and Sean continuing to study the Puna, just because we are finally getting an idea that the timescales are longer than any of us had anticipated when we started looking.
Yeah, right.
I'm retired, so I'm not going to be going back to the Puna, but some of Sean's or Mauro's students will. Hopefully Sean and Mauro will.
Absolutely.
I hope they try to confirm our latest set of results. Why? Because we published a paper in 2016 where we had used 3 instead of 5 anemometers, and our reviewers were pretty concerned. We didn't have enough anemometers, is what they were saying.
Yeah, basically.
Interestingly, in that 2016 paper, our conclusion was that the average aerodynamic roughness height was 1 centimeter, and closer or in the vicinity of the bigger ripples, it went to 4.
Larger.
What did we get from this 2018 study? It's about 1 centimeter pretty much everywhere, but when the ripple features exceed 50 centimeters in height, that's when we began to see these 2 to 4 centimeter roughnesses. So we think that the wind flowing over the mega ripples is beginning to become important when they're big enough.
Nice. Very nice.
So to follow up on your question, are there places where they're bigger than these guys? Not many. Okay. Before I retired, I worked with an Iranian graduate student who was very diligent at finding these kinds of things elsewhere. She found wonderful fields of large ripples in Iran and in Libya.
Cool.
But you might recognize it's rather difficult for Americans to get to either of those.
It would be a little difficult. Time to enlist your international collaborators.
Yep.
Very good. Very nice. Well, it's part of science. We do our work and we hand off to the next generation, and they verify and they carry on, and it's the cycle of life.
But it gets back to, you mentioned Titan. We are going to have some interesting Aeolian studies when the spacecraft, but it's basically a pretty sophisticated drone, a big one, will be on Titan. And one of the colleagues I've been able to work with several years, Ralph Lorenz, is involved in it. He's already thinking up some very fascinating ideas to, when they have flown to a new site on Titan, they will cycle the propellers up and down and try and stimulate sand movement.
Okay.
No one had really considered that until Ralph came up with the possible experiment. So I'm waiting. Unfortunately, if I remember the timeline, we're talking 2038.
Yeah.
Before this device gets to Titan. It's just the outer solar system is a long ways away.
Yeah.
But the questions are there. I hope the young people who might look at this paper will say, gee, I wonder what the aerodynamic roughness height might be on Titan, and figure out a way to try and measure it.
Very good. Very cool. Lovely, lovely. Well, I really look forward to seeing this topic develop over the next several years and beyond that into the decadals. So it's all very good.
Yep.
So Jim, thank you so much once again for talking with us about your very lovely article.
It's been a pleasure to be here and talk about something I'm excited about.
Oh, yes. And that'll do, everyone. And I hope this made your planetary science and astronomy day just a little bit better. And we will see you on the next one. Bye-bye.